Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning, and wish you and your family a very happy new year 2016. Our first video in 2016 will be on interference feed, and right now on my screen what you see is the interference feed between a steel shaft and a brass bushing. And this particular problem involve interference feed, so this will be involve a contact and how to get a interference feed done in a Abaqus CAE using Abaqus Standard. So let's get started. So we are going to do a shrink interference or shrink feed simulation in Abaqus Standard. Now interference feed, lot of we have seen this interference feed in we are learn in our mechanical engineering, is also known as a press feed or a friction feed. So there are two parts which are fastened together using a friction, and after the parts are pushed together they are fastened using a friction. And mainly you do googling, you find a lot of information in this. So there are typical example for interference feed is a bearing or bearing into their housing, attachment of watertight containers to the cable, shaft and bushing fittings. So a lot of things you see in the interference feed. Now typical problem we are going to do is we'll have a shaft, steel shaft, which will be 50 millimeter diameter. Since it is a steel shaft, we are going to build this as a rigid surface. So we'll have a shell thing which will assume as a rigid, and there will be a bushing whose total length will be 20, inner diameter is 49.4. so there is an interference feed of 0.3 between a shaft and the bearing, and outer diameter of bushing is around 50 millimeter. The bushing will be made up of brass, and typical brass, if you see, modulus is around 100 MPa. So we'll build bushing brass, and you can see a lot of interference decision making when you do interference feed. What should be the bushing inner diameter, what should be the shaft outer diameter, what should be the contact pressure to be generated, how much should be the stresses generated on the bushing and shaft. Some cases what you see where my cursor is there is a bond shrink feed, where actually people do a heating to the bushing, so because of temperature it get expand and then they push the shaft. So this particular problem will do. Also, if you see, there are a lot of specialized software in an interface feed calculation, where you give modulus of elasticity, Poisson's ratio, what will be the minimum and maximum diameter, and this particular software calculate what is the interference feed, what is the contact pressure, what is the tangential stresses on the inner and outer member. So a lot of specialized tools are there available, but Abaqus Standard is more capable to do this. There is a specialized interference feed available in Abaqus Standard, so we are going to explore that. The steps which we are going to do, will do a geometry creation for shaft, then we'll get a metal and property creation, will assign to this shaft and bushing, we'll do a mesh generation, analytical rigid surface, we'll do a contact definition, normal contact definition, then we'll learn how to do an interface feed connection to this contact definition. Then you'll see a lot of boundary conditions will give for this. Non-linear static steps will do step definition, output, will submit a run. I'll just emphasize two things. We'll do a normal contact pair, surface to surface, and then we'll convert into star contact interface shrink feed, and then you'll see how this shrink feed is going to do. So let's get started. So I'll start with new. So we'll start with Abaqus 6.113. So let me first set up a working directory interference feed demo. So I'll set a working directory interface demo. So I'll set that. Now we'll quickly create a part. We'll create a shaft. So since it is a solid steel shaft, we are going to build it as a discrete rigid surface. We are going to use a shell, we'll go to extrusion, and approximate side will put 200. So once you put that, you see you get all this grid. Then I'll quickly put a xy 0, 0, then 25, 0, and then 0, 25, Then I'll just select this create a arc, center and two end points. So I'll select the center, I'll select the first point and the second point. So I'm done with shaft. So I'll then do extrusion, which will be like a 100 depth. So this is a shaft create. I'll just quickly go 2 minutes back to the problem. Now you see in this problem I had taken the advantage of a quarter symmetry. So instead of modeling whole shaft, we can build a quarter model, or quarter model again we can use 1/8 model. So we are going to build just 1/8 model, and based on 1/8 model we'll just build this, try to solve this problem. So we'll reduce the simulation time. So this is now shaft we are done. I'll just quickly go and then I'll just cut the shaft because we want a contact region. So I'll go with a datum creation. So now why we want a datum? We want to split the surface so we can have a easy to choose a master and slave. So I'll just go to create datum plane. Now I want to take XY plane. I'll just offset it by 15. So you can see a datum plane there. I quickly split it with datum. So I go to partial face, use datum plane. I select a datum plane and I say create a portion. So immediately it is cut. So guys, I'm done with shaft. We have just cut this so that we can get some surface generation there. So I'll say quickly create. So this will be like my master surface. So I selected that surface. Done. So now since it is selected, is asking me which will be my master, which should be my shell face. So I want to take outer face. So it's a purple will be my S pos or S negative based on my brown or purple. So I've done this. I'll just quickly go to the tool and create a reference point, and I selected reference point somewhere here. So this will be my, since rigid surface, I'm going to give a boundary condition or reference point, and on that reference point will give a boundary condition which will be applicable for this all. So I'm done with shaft. Now I'll just quickly create a bushing. So bushing will be 3D deformable. I'm going to make a solid bushing extrusion. So now for bushing again I'll create a points 0, 0, then 24.7, 0. So we are going to give interference, and then 0, 24.7. So you see I created this chain. Now I'll create outer point 50, 0 and 0, 50. So I'll just quickly fit it. So this is what the 5 points you can see. Now I quickly generate a curve. I select a center point. I select the first point. I'll select the second point. First curve. Then again I'll choose center point. First point. I'll select the second point. I've done this. Then I'll just go to line creation. I'll select this first point. This is my second point. Then again I'll go to line creation. No, I'll just go to line creation. I'll select this and this. So now I've done this. So I'll say done, and then I'll just do 10 mm. The total width of the bushing is 20. Since we are making a 1/8 model, so the depth will be 10. So I'm done with this. Now I'll quickly create a material which will be brass. So it will be brass, and then I'll create elastic modulus 100 GPa. So 100 e power 03 is a MPa and 0.34 is a Poisson's ratio. And then I'll create a section quickly, a solid bushing homogeneous, continue, and then I'll select the metal brass. Now I quickly connect this section assignment to this bushing. So you see immediately color change. We'll also create a surface called a slave here. and I can choose this bottom portion. So I created slave. Since it is a solid, it will create a face. Now guys, if you go back, I created a shaft, I created the section points, I created a master surface here. So as soon as you generate a part, you generate the surface or node set, whatever you want there. Now we'll quickly create instant. So create instant, shaft and bushing dependent, and say okay. So this is there. Now you can look into a part instance, so you can see there are two parts. So we created two surfaces also, master slave we created. Now we'll do a meshing first, and then we'll go to other things. So I go to meshing part wise. I'll select the first shaft, and then I select approximate global size is something like a 1.5, and then I say mesh. So quickly done a meshing for shaft. Now I'll create a bushing. For bushing I'll select a global size 1.0, and then I'll say quickly mesh it. So I created both meshes for shaft and bushing. Now one more thing I'll create the node set, because we are going to make a 1/8 model. So if I go part wise bushing, so let me put in some view. So like we'll have one particular face which will be constrained in z-axis, then you have y-axis symmetry and x-axis symmetry. So I'll create immediately a node set. So for bushing I'll go to bushing, and then we'll go to the part bushing, and or we'll better go to assembly, so that is better for us to select. And then we'll create a set, and we'll put a x symmetry. We'll select a geometry. So this surface will be x symmetry. So let me select that. So done. So this will be x symmetry set. So I'll delete this. I'll create a set x symmetry node base. I'll create. So I'll put in some view. So this will be x symmetry. So this is done. I'll create one more y symmetry. Again node base I'll create. Done. So we have created x and y. Now we have to really look for one more. This will be a z symmetry. So let me first check in assembly how it looks. So if I put in assembly, you see positive y, this face is a z symmetry. So I'll put again part. So this is my face, which should be y symmetry. So I'll create z symmetry. I'll create a z symmetry geometry base. I select this. Done. So I created 3 node sets. 2 are node base, one is a face geometry base. You can have anything, but just to give a flavor what different option we have created 2 node base, so you can also learn how to use a node base and the surface base. It's no harm if you use all for surface base. So we created that. We created instant. Now we'll quickly created a and we'll go to contact. So we'll create a contact property. I'll say friction contact, and then mechanical tangential. Here we'll say penalty based friction. The point one is a friction we are using. So we have created a friction. Now I'll just quickly go back to the steps. So guys, if you create a geometry, material, property creation, we generate a mesh, we generate an, now we are generate a contact base also. Now we'll move to our next boundary condition, but first we'll define a contact. So now I'll go to the interface, I'll say create. It will be contact pair, so it will be contact, surface to surface contact, and the master surface will be the shaft, which we highlighted, continue, and then the slave surface will be bushing, so continue. So we have created the friction. Now this is a normal contact we have defined. Then we'll also define a boundary condition. So we'll create a boundary condition. So X symmetry. So I'll use a symmetry, and then I say X symmetry, continue, and then I'll say X symmetry. So X displacement and Y and Z rotation will be constant. So I created that. I'll create Y symmetry. So it will be Y symmetry, and then Y displacement and X and Z rotation will be constant. And then I'll create one more, which will be Z symmetry. Now we created Z symmetry. Now shaft we have put constant, so shaft will be end caster. So I'll create one more. It will be end. It will be end caster. End caster means it will be all constant. All degree of freedom will be constant. So we'll select that point, done, and we'll put all displacement and translation constant. So this is what boundary condition we have done. So we also created contact, we have created boundary condition. Now we'll quickly create a step. So we'll create a step. It is interference fit. Static general, and the NL jump on interference fit. Increment will start with 0.01 and minimum will be 1 e power 0.5, maximum will be 1. So we have created interference fit. Now we have created everything. Now here is a step actually important for the interference fit, and this is the game actually you have to learn. So you have to define a normal contact, and then you create a step, and then in step you define this is a interference fit. So now everything is done. So you again go to contact, where you define a contact. Interaction, you go to contact, you say edit it. Now you see this option is highlighted here, interference fit. So click on that. You say it's an interference fit option. You say gradually remove the slave node overclosure during the step, automatic shrink fit, and you say OK. So now this particular problem is now become an interference fit problem. You define a normal contact, and then define the step, and then later on you just edit these two interference fit. So guys, we have done everything. So now we'll just quickly check it. So we'll create a job. So say create, this will be interference fit example. We'll say continue. Okay, and then we'll quickly do a data check. So looked into, it's going into data check. So we can also quickly check how the input file looks like. So if you see here, now contact interference, shrink fit, bushing you have seen here. So this is inside the step. So interference fit option will be inside the step, and then you see there will be a normal contact outside the step. So you define outside the step the normal contact pair, then you define a step, and then inside the step you define this as an interference fit, and it is a shrink fit. So you have different option how you are going to how you are going to reduce this interference fit. So in this particulars we are defining as a shrink fit, or you can give amplitude how we are going to reduce this interference fit over a period of time. So we had done this. So interference data check is done. So we'll submit a run. So let's hope. So this is continue. So we'll just wait for let the analysis get complete. So once we get we'll just wait for this. Now friends, I have just loaded the results. We have just completed the run. So I just check a STF file, and you can see in STF file you can see a severe discontinuity iteration, then equilibrium iteration. So there was all the time over a period of time all the interference fit of 0.3 around the circumference has been removed, and you can see how the von Mises stress generated in a bushing. Now this is just 1/8 model. So I'll just show you how you can just 1/8 model, how you can take it a full model. So let me check where you can do this. So you see here my cursor is there, ODB display option, you see mirror pattern. Now you put all XY, XZ and YZ, apply, and you can see this is a full model. So this is just a learning. You can just build a model as you just build a 1/8 model or 1/4 model, and you can just mirror it, and that's what you can see it. So guys, we have just shown you how to do interference fit analysis using Abaqus Standard. So it is straightforward. You just define a normal contact, and then in step you define interference contact. So thanks for watching this video. Guys, this is a non-profit project, so we would like your support to take it forward. So don't forget to like us or give your comment, and don't forget to subscribe us. Thank you. Bye bye.